So hello, everyone. I'm really excited to be here at ADC. Big thanks to the organizers for the opportunity to present our work. I'm Nikhil. I work on audio algorithms for hardware products at Google.
My name is Wilson, and I am an electronic music enthusiast currently working at Waymo.
And today we are here to present DDSP-VST, a cross-platform audio plugin powered by machine learning. So this talk is split up into the following sections. We'll begin with a brief introduction on what DDSP is, and then we'll dive into some of the engineering and UX challenges of turning this into a real-time interactive experience that can be used by artists and musicians. So DDSP stands for Differentiable Digital Signal Processing. It lets you combine the interpretable structure of DSP elements, like filters, oscillators, with the expressivity of deep learning. For this project, we leverage DDSP for timbre transfer, wherein you can transform a given audio signal into any musical instrument using its extracted features like pitch and loudness. Here's a really cool demo by one of the original authors of the paper, Hanoi. Awesome. So since 2020, we've been able to leverage DDSP's efficiency to power a variety of creative web experiences and offline demos. However, there's one question that we always got. That's really cool. When can we get that plugin? So how do we turn this offline research experiment into an engaging and interactive experience? This talk aims to address the engineering challenges in that. So we arrived at the following requirements for this plugin. It needs to be cross-platform. It needs to run in real time for experimentation and live performances. It needs to provide intuitive controls for the parameters for timbre transfer. And lastly, it needs to be customizable so that users can upload a piece of audio, train their own models, and drop it directly into the plugin.
But before that, I'm going to give a quick primer on the underlying magic that powers DDSP. So the core concept of DDSP and almost all machine learning, in fact, is that as long as a function is differentiable, you can propagate the gradients of a loss function across that function to modulate the weights of a learned machine learning model. Well, it turns out a lot of DSP primitives, such as additive synthesis, FFTs, and FIRs, are in fact differentiable and can be composed in interesting ways to form an end-to-end synthesizer. So how can this be used in an audio context, in the context of timbre transfer? Well, in the original DDSP paper, there are three main components. The first component is this encoder stage where we extract interpretable features from the target audio, such as pitch and loudness. This then goes into the decoder stage where we output the harmonic amplitudes and filter noise coefficients. These outputs go into the last and final synthesis stage, in which it is used to resynthesize the target audio. So where does DDSP come into play? The thing I want to draw attention to is the synthesis stage, this third modular component. By making these individual components differentiable, you could then learn a unique instrument model, a black box ML algorithm that captures the unique timbral characteristics of an instrument, learned by making it reconstruct a 10-minute segment of audio. After training, this specific model can be exported and then reused in a real-time inference context, in which every other module, specifically the encoder and synthesis modules, can be replaced with any other functional analog. So that's kind of the magic of DDSP, where you could hot swap these components with their non-machine learning counterparts. So that's a really quick primer of DDSP, and if you want a more in-depth explanation, please check out David Trevelyan's talk at ADC 2022. Now, DDSP isn't the main focus of the talk. I think the main focus is how we actually turn this to work in a real-time plugin. All right.
All right, so Let's take a look at our stack. Have you all heard of JUCE? So we use JUCE to build a cross-platform part of the audio plugin. And then for model inference, we chose TF Lite. There's two reasons behind this. One, TF Lite allows us to use our trained models in a way that's optimized for inference across major OSs. And secondly, DDSP was originally built using TensorFlow, and it's pretty straightforward to convert like TF models to TF Lite models. And lastly, it was complicated to integrate TF Lite with JUCE initially. This was because TF Lite was built using Bazel, and this caused a lot of hair pulling, especially on Windows. So we were quite excited when both JUCE and TF Lite added support for CMake. It made the build process seamless and led to a significant boost in productivity.
So next, I'm going to talk about some of the real-time challenges in getting this model to work in real time. And if you work in real-time audio, then you deal with strongly timed audio callbacks. And to give a quick primer, every set amount of milliseconds, your audio card says, hey, please fill this audio buffer with ones and zeros. And if you don't, I'm going to play anyways. And if you don't fill it in time, called a buffer underrun, bad things happen. This usually involves in glitchy noise sound, or maybe you might pop your listener's eardrums. That's not good. So what does this mean in the context of AI? It means that the AI inference speed actually matters, since we have a finite amount of CPU cycles per input frame. So there was a lot of care in actually reducing the inference latency of all of our three components. First, I want to talk about the F0 or pitch encoder. So as we said before, we could substitute these components with any real-time analog. So we actually tried different real-time pitch detection algorithms, such as Yin and Spice. However, we noticed that our trained model was extremely susceptible to bad pitch detection. So this usually manifested itself with octave jumps and jittery pitches. And we realized the end result just did not sound good. There were a lot of phasey artifacts, and this is not a good product that someone could use in a real performance. So we realized we had to use the original model used in the original DDSP paper, and that was the CREP-full model. But there was a problem. The inference time was too long to be used in a real-time context. So we settled on the solution of distillation. What distillation is we trained a tinier CREP model called CREP micro with only 160,000 parameters. This was done by training it to predict the logits of the largest CREP full model. And this was crucial in reducing plugin latency from over 500 milliseconds to 64 milliseconds. There were also a lot of non-trivial changes in the instrument decoder. We noticed in the start that we trained a much smaller recurrent neural network than the original paper, and found that we could increase the time between predictions from 4 milliseconds to 20 milliseconds without much change in audio quality. This meant a 5x boost in efficiency, since we were making 5 times less TF Lite inference calls. We also had to pay special attention to not incorporate any non-causal convolutions, like the web versions of DDSP. And this is because the original offline model was able to look into the future. Obviously, you can't do that in a real-time context, so if you could look into the future in real time, well, you deserve a Nobel Prize. So we modified this to be non-causal. We also had to fight TF Lite in the meantime, and if you worked with TF Lite before, you know that TF Lite has a limited selection of built-in operators. However, a lot of our operators in the original DDSP paper relied on were not supported in TF Lite. So we actually had to iterate on different types of stateful neural networks, such as LSTMs and GRUs. We settled on the GRU, which is a gated recurrent unit, and also had to store the state natively in C++. All of this resulted in a TF Lite binary reduction from 150 megabytes to 5 megabytes.
All right, so that was the pitch encoder and the instrument decoder. Now let's talk about the synthesis. So the synthesis consists of two components, the harmonic audio and the filtered white noise. The parameters for the synthesis are generated from the instrument model. That's 60 harmonic components for the additive synthesis and 64 noise magnitudes for filtering white noise. We replaced the differentiable TF Lite model with more performant DSP components implemented natively in C++. And this was one of the original intentions of the DDSP paper. This native implementation improved the performance by about half compared to the TF Lite model. All right, putting it all together, how do we actually make this plugin run in real time? So one of the implementation challenges that we faced was differing frame rates. So we have two processes that are running at different rates. The audio callback runs at a variable rate, as it depends on the sample rate and block size selected by the user. And the model inference runs at a fixed rate of 20 milliseconds. We solved this problem by using resamplers and FIFOs appropriately at the input and output stages, as well as running inference on a separate thread. Here's a block diagram of our overall plugin architecture. So just take you through it. You get a chunk of input audio that gets pushed into the FIFO. Our end-to-end training in the Colab was done at 16 kilohertz, so we downsampled to 16 kilohertz. And now we run inference on the modified models we touched upon previously. And we generate a chunk of synthesized audio. We resample this back to the sample rate selected by the user, push it in the output FIFO, and then the audio callback pulls the appropriate number of samples from this FIFO. Now, at this point, we were running everything on the audio thread, but we ran into a problem where we were hearing audible glitches for smaller block sizes. In a typical DSP use case, the amount of computational load scales with the user block size. However, for us, the computational load is fixed for 64 milliseconds worth of audio data. So we decoupled the ML inference from the audio callback, and we achieved this by running inference on a separate thread at an interval of 20 milliseconds. This also resulted in consistent behavior across OSs for a given combination of block size and sample rate.
Cool, now we have a working real-time plugin. The next question is usability. So one of our guiding goals at Magenta has always been to democratize machine learning for artists and musicians, empowering creatives to decide for themselves how to use this new technology in their creative process. So besides the default models that we provide, we also allow users to train and use their own custom model. However, there's a problem. Not everyone has a beefy $2,000 GPU lying in their basement, especially an everyday artist. So to solve this problem, we actually created a custom Colab notebook that anyone can use. So to use this notebook, anyone could, click this link, upload a 10-minute snippet of monophonic audio, hit train, and this will send it to some random Google server running in Montana, and it'll spit out a TF Lite model that you could drag and drop into this VST. So this allows anyone to train their own TF Lite and DDSP model.
Okay, so the next section of usability is UX. So each instrument has its own range for pitch and loudness. Flutes play high, basses play low. But what happens when you feed lower pitches into a model that's been trained on higher pitches? We get some fun, cool new textures. And with that, we introduce tone shaping, a control that allows us to easily explore the space of sounds. So what you see here, the bouncing ball is a visual indicator of our current pitch and volume. You see this when you're playing real time or just playing back. The range of volumes and pitches the model was trained on are shown by the highlighted box. It's a little hard to see that on this screen. Maybe on that screen you can see it's like a highlighted purple box. When the ball is inside the box, we can expect a faithful reproduction of the timbre. And when it's outside the box, you can hear how the prediction breaks down in fun and creative ways. And we enable this by modifying the Colab to save this model metadata, that's the pitch and loudness ranges, in a way that's interpretable by our VST. All right, here we have a demo on how tone shaping works. going through DDSP. Now we turn it on. That's resynthesizing the same thing. Change it to a flute model. So now you can see that the ball is kind of in that highlighted region. But you can also drag that box and do fun stuff with it. So as it moves to the left, you kind of hear a low pass effect. As you move to the right, you kind of hear like the higher harmonics being added in. All right. Oops. All right, and here we have Jesse playing the guitar and changing some timbres. Hard to see which model it is. It's clarinet, it's a melodica, trumpet, violin. And next, so we were scouring YouTube, and we found this really cool demo that a user uploaded. A quick look at that. So that's a guitar that's being transformed into a saxophone. It's one of our most popular models. And lastly, this plugin was used live at the Google I/O 2022 pre-show by the artist Miha. Got a quick video here. Oops. Oh. In the interest of time, we'll skip this one.
You can trust us.
Yeah. All right. Next steps.
Yeah, so if you guys watched the clip earlier, DDSP-VST works and was able to be used at the 2022 I/O pre-show. So what are the next steps? I think there's a lot of lower hanging fruit to really improve on this plugin. So I think the first step is better pitch detection. As we said before, kind of due to the way we shifted things to be non-causal and how we really distilled the pitch detection algorithm, we still hear a lot of phasey and zippering artifacts in the plugin. So if anyone has any ideas on how to do better real-time detection, like we're all ears. We could also improve the rendering quality by running inference at a higher sample rate. As we said before, inference was running at 16 kilohertz, so we could probably bump it up to 44K. We could also improve plugin by enabling GPU support, probably for both the GUI as well as TF Lite inference. And lastly, the original DDSP model, there's a learned impulse response for the convolutional reverb. So another option is to make this even more realistic to the original audio that it was trained on, is to store the impulse response in the model itself, somehow in TF Lite.
And here are some links if you'd like to learn more about the project or check out the code. It's all open source. And another benefit here is that if you want a reference for building machine learning plugins with JUCE and TF Lite or any other ML framework for that matter, please check it out.
Yeah, and something I do want to call out here is although you don't have to use TF Lite as your inference framework, a lot of the lessons here can be reused if you want to do neural audio synthesis, such as distillation, and really cutting down the inference time of your model, and also how to deal with different frame rates.
Right.
Yeah, thank you. This was a massive cross-functional effort in collaboration with the Magenta team. So thank you, Megan, Jesse, Soren, Seimon, and many others that helped. Yeah, thank you so much for listening.
Yeah. And we'll take a couple of questions. A bunch of questions.
Hey, great talk. For your pitch detection, I've seen some people use like self-supervised learning to try to get better quality pitch detection. Do you consider this for replacing your pitch detection model?
Great question. And I think that is the SPICE model, which also came out of Google research. I think it's a self-supervised, if I remember correctly. It did work great, but it was pretty heavy.
I will also say there has been a lot of developments in audio since 2 years, since we made a lot of engineering decisions during the architecting of this model. So the state of the art might be massively different, but I do see a lot of space, especially if there's an open source foundational model for audio being used in the context of pitch detection. So probably in the future, if I remember correctly, CREP was made in 2018.
Yeah.
So 5 years old, and that's like a millennia in AI world.
Hi. So my question is, I guess my understanding from what you presented is the decoder is basically creating parameters for an oscillator bank and a filter bank on this noise, and then you're rendering that audio still in the inference thread. So my question is, why don't you just pass those parameters to the audio thread and actually run those traditional DSP blocks on the audio thread instead? Would that not solve the sample rate issue that you were mentioning?
You can, and it's just something we haven't gotten around to. And so, yeah, you're right. So since it's all done end to end, we just kept it all as one block. So you decode the pitch, do DDSP, and then do the synthesis. Even though it's being done natively in C++, it's all being done in one function. But yes, you can absolutely do that on the audio thread as well.
I think we actually tried that at some point, but didn't watch enough ADC talks on how to do programming. So I think that question, yes. Now with the knowledge that we have now, I think to the second question, I think the frame rate differential still exists. So you still have to kind of manage different frame rates on what the model was trained on, and I think that's still a problem.
How feasible is this to work with other synthesis models if you don't want to be like so faithful to the original? Like you want to have imposed like a quality of like, can you use this with FM or wave shaping or other kinds of things?
That is a great question. I don't know if I have the right answer, but I would think yes. It just comes down to how you transform those harmonic components and the noise magnitudes. So how do you render that?
I think it's also really how you recompose those differentiable elements and in unique ways, as long as, I think the core concept here is as long as the composition is differentiable, then you can learn whatever your arbitrary black box ML function, that's more upstream. So if you have a way to rewrite, say, FM synthesis or wave shaping, I would guess that it's possible. I hope so.
Any opportunity to use MT3 to start doing poly note detection with DDSP?
That would be a question for Jesse, but I'm not sure.
I think off the top of my head, currently how DDSP operates is monophonic, so I think there might have to be bigger changes to the overall model to get things working end to end. Basically re-architecting the entirety of the paper.
Got it. Thank you.
Thank you so much.